Awesome. All right. Hello, everybody. My name is Shahrukh. I'm product lead at Eco. Joining me is also Captain Ku, also known as Kirill. And joining us remotely is our lead technical product manager, Christian. Now, Christian really wanted to be here, but he's having a kid anytime, like in a couple of days. So he really couldn't make the Denver trip, but he really wanted to be here. So I'm hoping all of you can accommodate him joining remotely. Christian, come off mute. Can you hear us?
Hi, everyone.
All right, perfect. Awesome. So before we start, I just want to give a quick overview of what we're going to be covering in this presentation. So first, we want to talk about one of the products that we've been building called Routes. And we want to talk about why we built it, why we think it's very useful and compelling. And once we get into the origin story, we want to talk about, as we started to build Routes, some of the problems we ran into it, and some of the problems that led us to finding out Polymer and the amazing opportunity that we saw combining our product with their technologies and all the exciting things that we could do together. So before we get started and talk about Routes, I want to talk a little bit about who we are. So at Eco, our mission is quite simple. We want to translate every single on-chain experience into a one-click stable send. And this objective should not surprise anybody. If you've ever used like conventional Web2 applications like Amazon or Stripe, you know that a lot of these companies, the giants of the space in payments, have made a lot of investments in making sure that the payment flow has the least amounts of steps possible for the user, because they have done a lot of research that shows that the more number of steps you have in a payment flow, it leads to poorer conversions and it leads to more user attrition. And so at Eco, we want to enable the same kind of user experience for on-chain products. And that's pretty simple. And the reason we built Routes is we actually needed it. If you might remember, for those of you who have heard of Bend, we were actually building a payment app first. We weren't even in the infra space. We were trying to use some of the amazing abstraction technologies to build a payment product that used stablecoins. And we were actually one of the first wallets that launched when 437 went live on mainnet. So we were actually one of the first ones to implement it, and we actually showed it at ETHCC in 2023. Some of our members are there who actually did the demo. And Bend out of the box was only deployed on Optimism, but it already had a great set of abstractions. So for private key abstractions, we were using Shami's secret sharing, keeping it non-custodial. And so users could have access to their keys. We had no control over it, and they had a fully non-custodial product. We also did gas abstraction using 437, which seems easier today, but when 437 first came out, paymasters were very basic. So all the validation on like gas policies, we had to build it all ourselves. And we actually talked to a lot of the infra people that you use today, and a lot of feedback we gave them informed the products that are built today. So we did that early on. We were very proud of it. And then the other thing that we did, the third set of abstraction, which was really cool, was token abstraction. And token abstraction is our thesis that there's going to be an explosion of stablecoins, different types of stablecoins issued by different entities. So the user doesn't need to worry about that. Like, think about this concept. It's only true in crypto, but think about the concept of the user thinking that one piece of dollar is different than another piece of dollar. Like, that doesn't really make sense at all. So in Bend, what we did was, regardless if you have USDC or USDT, we basically aggregated it into a single balance. And we deployed it on Optimism. We showed it at ETC, and it was amazing. We thought L2s are the future. Scaling is finally here for Ethereum. We love 437, the abstractions that it enabled. And we were so excited. So when Base launched, we were like, hey, what if we extend the concept of abstraction to also abstract chains themselves? And that's where the problem started to happen. Because we realized that if we wanted to create a product that had the same security that we were enjoying being on a rollup, so we couldn't find a single solution that leveraged the properties of Ethereum or the security of Ethereum or the liveness of Ethereum and was flexible enough for our use case, could be deployed permissionlessly for all the chains we wanted to go on, there just wasn't anything there. And so just 1 year ago at ETHDenver, we presented a concept. And this concept was called the native route. It built on this insight that all L2s or L3s, all rollups, basically settle on Ethereum. So we realized that Ethereum acted as the single source of truth that allowed us to communicate between rollups, which is the same concept that rollups use, moving funds from Ethereum into themselves or exiting from the rollup into Ethereum. So what we realized that because all rollups settle on Ethereum, from the Ethereum state root, we can derive the state of any destination rollup that settles on Ethereum. So last year at Base House, we actually presented this concept, and the flow is pretty simple. We combined an intent-based design with this insight about leveraging Ethereum, and we created a transfer protocol that allowed a user, if you wanted to transfer from Optimism to Base, it allows a user to create an intent on Optimism. A solver can just execute that on Base, and then the solver waits for the Base state root to be finalized on Ethereum. And then once that state root is finalized, because OP chains expose the L1 block hash, Optimism knows the Ethereum world state where the base's state root was finalized. So what you can do is you can make a contract that actually takes that L1 block hash, constructs the Ethereum world state, then from that world state constructs the base world state, and then from that uses a storage proof to actually validate if the intent was executed or not. And that is pretty freaking cool. That has the same security as the rollups themselves. It has the same liveness as the rollups themselves. So it is exactly as using a native bridge going from parent to an L2 or an L3. It has the same security and liveness guarantees. There is no trust because it's fully cryptographically verified. And when we built it, we were super, super excited about it. We were so excited, in fact, that we productionized it and we launched it and integrated in Bend. And that's when we started to run into some problems. And to tell us about our storage proof blues, as we call it, I'm going to kick it to Captain Cook. And Captain Cook, if you want to talk about some of the issues we ran into implementing the native route.
Yes. Again, so we have a route that's going from Base to Optimism. And first, we basically prove the state of Ethereum itself on Optimism, and then Base derived from that thing. And it was working. We finally made it work and everything happening, but it was super expensive. It was economically unviable because the size of the proof was insane, and you had to scale your intent system to many, many intents to be able to be profitable there. And another thing is, if we are going from L2 back to Ethereum and trying to withdraw something, users can get stuck for 7 days. And with L3, it can extend up to 14 days. And another thing is not all L2s are the same. So for example, Arbitrum, it does not expose state of Ethereum. And you cannot use the same system that you build for Optimism Base, you cannot use it for Arbitrum. And some L2s, basically, even the storage and structure within the contracts that present different L2s are different. That's why they're incompatible. And on top of it, the actual cost, we put it for the last, it was insane. It was, I'm going to tell you how much it was right here. So if you look at the flow of the proof, you pretty much have like a 6 or 7-fold where you prove things starting from OP, and then Ethereum again, then you go to another L2, and then on the settlement, when you need to prove everything, you basically need to provide 16 kilobytes of data, and which is over 500 instances of bytes 32, and that is just could not work for us. And gladfully and thankfully, we found Polymer and how to use Polymer to solve that problem.
Awesome. Yeah. So before I kick it to Christian to talk about where Polymer fits into the picture, we kind of went as far as we could take it. And then because we realized that the outcome of this, especially relevant from the previous talk, is that this impacts the price the solver will quote when fulfilling an intent. Because the solver is waiting 7 days for their funds to actually settle, they have a 7-day opportunity cost. So although this is really secure and everybody loves it, the trade-off is that the capital inefficiency basically leads to prices that when you look at competitive transfer protocols, we're just not even close. We're not going to be even close to the marker. So that is why we stopped we actually didn't use this in production. We actually defaulted to using a general AMB, which was actually Hyperlane, which did fit our criteria because it was permissionless and still giving us a lot of the things that we wanted and a lot of flexibility we wanted, but we still were enamored by this vision of leveraging Ethereum to kind of enable this transfers. So talking about how we can do that with Polymer, I'm going to kick it to Christian. Hopefully this transition works. Christian, take it away.
All right, what's up, everyone? I hope you can hear me. Shahrukh, thumbs up if you can hear me. All right, cool. Yeah, so we still had this vision, like all this block hash data is basically being exposed on Ethereum, and there must be some system that allows it to efficiently ingest that block hash data and use it to prove intents. So that's when we met Polymer. We met Polymer at Bangkok, and it was awesome. And Polymer, what they basically do is they ingest block headers from all of the rollups that they support, and then they process those block headers into very efficient data structures that can be efficiently consumed by proofs, by applications. So the tree they use is called an IAVL tree. And if you think of the Merkle-Patricia tree as this like nested Russian doll proof, where you're proving like 3 layers down and it's super expensive, the IAVL tree is a very, very efficient packing. So you can actually prove an event happening or something happening in that tree very easily. And so just to show you kind of what that looks like, we actually have a little demo that we recorded of using Polymer to solve some intents.
So this is Christian over the weekend with a lot of coffee, hacking away at a POC.
Hey everyone, what's going on? Sorry I can't be at ETHDenver, but I thought I would record this demonstration of the use of Polymer in our intent system. So I'm just going to walk you through at a high level what actually is happening here. First, a user is going to create an intent on Optimism on our intent source contract. Then on base, the solver is going to come in and they're going to fulfill the intent. They're going to use the fulfill storage method, which is the exact same method we used before for our Merkle-Patricia trie system, and that's going to emit a to be proven event. Then the solver is going to go to Optimism and they're going to request from Polymer a proof of the event on base, which they're going to submit to the Polymer prover, which will mark the intent as complete. And finally, the solver is going to withdraw the rewards. So let's just show you what that whole process looks like. Hopefully I can keep up with the script, but let's run it now. All right, we're going to connect to Optimism and base first, and then we're going to originate the intent. So the user is going to go to the intent source contract, and they're going to basically say, I want to give $1.1 to the first person who pays someone on base $1. And you'll see that data there. Then the solver is going to come in on the inbox now that the intent is originated, and they're going to solve that intent. And when they solve that intent, it's going to emit the to be proven event. Now that that's emitted, we can go to Polymer and we can request a proof of that log, which we now have. And we're going to submit that log to the Polymer prover in hex. Done. Now it's been validated. The proof has been validated on the Polymer prover, and the intent is marked as fulfilled. And now the solver has withdrawn their intent. And you got to see there how like blazingly fast this whole system is. Obviously, it runs Apolia, but still, you can imagine, you know, a pretty close level of speed to what you just saw there. Awesome. So now we're going to walk through the same thing, but we're going to use a batch system. I think this is super cool. So here, same thing. We're going to create intents, but we're actually going to create 20 of them on the origin chain on OP. And then on base, we're going to fulfill all 20 of them, but we're going to fulfill them with what's called a silent method. So there's no emits. It's just going to get fulfilled. And then in step 3, the solver is going to come in and do a batch storage emit. And this is basically going to take all of the intents that have been fulfilled and pack them in a super tight structure of the intent hash with the claimant, which will be relayed to the origin chain, Optimism in this case. Then the solver still just requests one proof from Polymer and submits that proof to the validate packed function, which will like essentially destruct the packed array and mark all 20 intents as fulfilled, and then the solver will withdraw the rewards. Just to show you a little bit about what that actually looks like, here this is the batch storage event. It just takes a destination chain ID and an array of intent hashes and then packs them really tightly in this batch to be proven event. It's just the destination chain ID and the message body, which is just a bytes object. And then the Polymer prover over here accepts the packed proof and extracts it using this decode message body method, which just destructs the entire bytes object. Anyways, I'll show you what that looks like now. I'm going to start it. I'm probably just going to pause it and come back because it takes a while because we're doing 20 intents. So yeah, you'll see the intent start, but yeah, I'm just going to pause it. So the script is done running. You can actually see here, we did 20 intent originations and then 20 fulfillments. We emitted just kind of a massive bytes object, got a single proof from Polymer, and then validated 20 of intents with a single proof in one transaction. So that gives you the power of what Polymer can offer. We might fulfill 20 intents in separate transactions, but we can do a single emit and a single proof to mark them all as actually filled on the origin chain. Thank you so much for this demo.
Switch it back, Christian. Are you with us?
Next slide. Let's talk a little bit about the kind of some of the results we saw when we did the gas analysis. So like batching in 20, we're able to improve the gas efficiency per intent by 4.6x, which is really good from an execution perspective, but way better, we actually were able to reduce the total, next slide please. We're able to reduce the total amount per intent by 13.5, so the actual call data size as viewed from the L1 was reduced by 13.5. Next slide, and even more importantly, I know I need to hurry, emits rock. Polymer gave us stuff back in 2 to 4 seconds. It was super easy to integrate. We did the prototype in a day. And compared to the Merkle tree, Polymer just blew it out of the water. The 20 batch actually was 123 times more efficient from a data perspective. So if I go to the next slide, the most important thing though is I actually think Polymer can enable something even greater than what we did. And I want to call this solving the n-1 squared problem. So if you're using a traditional message bridge, you have to send n-1 squared messages, right? If I have 11 rollups, I'm going to have to send 10 times 10, 100 messages every 30 minutes to update the state of my application. However, what you can do with Polymer is you can actually pack all of the intents for all the chains into like a very efficient tree and just broadcast that single tree. Then the proof that you get of that tree's existence on the chain you care about can be ingested by all the different rollups all at the same time with one proof. So you actually just do one emit, one proof, and then you can actually provide that proof and the specific leaf data you care about on every other destination chain, which makes it possible for Polymer to serve hundreds of rollups in a single proof. And then, that's what we're going to work on next.
Awesome. All right, almost done. So to recap, at Ecom, we're here to make every crypto action a single-click stable stand without the trade-offs. We really want to build an open permissionless system. So like we don't require any approval from our governance or protocol to deploy these things. You can just deploy them on your own. Many projects already have, because we want to build a framework that unites Ethereum. And we love Polymer because it allows us to do just that. So we're really bullish on what we're going to cook together with Polymer. Really excited about having a Polymer prover up on our portal, which is live right now in beta. So you're more than welcome to try, and you're going to see a Polymer prover up there pretty soon. And then once we get into the batching stuff, we're going to have some blog posts with Polymer, and keep your eyes peeled for that. And that's our talk. Thank you so much.